Okay, this video is going to be done in two parts, so let's get started. So this is H3O, vector velocity, speed, unit vector, relative position. So velocity is, we're going to be talking about velocity in vectors. So velocity is when it's a quantity that's in magnitude, and velocity also has a direction. So velocity is a vector with magnitude and direction. So for example, if you look at the two vectors that I've just drawn before right here, 10 meters per second north. So I've drawn here on this scale, it's 1 inch, right? So I've drawn this distance 1 inch representing 10 meters per second, and I've drawn this distance here 1 inch, going 10 meters per second east. So these are two different velocity vectors, both with the same magnitude length of 10 meters per second. Now, velocity, this length here, super, super, super important. It's going to come up later. People asked questions about this. The velocity vector has to have the length during 1 unit of time. So notice this is meters per second. So that's why it's 10. So if the time was seconds, then we would be using this magnitude. Okay. If it was hours, then this would be a lot longer. Okay. But 1 unit of time. Okay, so velocity has a direction and a magnitude. Speed, on the other hand, just has the magnitude. So we represent finding the magnitude with those absolute value signs. So if I'm using v for velocity, then for speed, I'm going to use velocity with the absolute value representing only the magnitude. Okay, so speed is the magnitude. Okay, all right, during 1 unit of time. Okay, so let's look at this first example. Consider a boat that is initially at point A with coordinates 5, 1. So my initial position is this. Okay, and we've seen this equation before, where it's r equals a plus bt, where a is the initial position and b is the direction. We've done this in previous handouts, but now we're going to apply it with some real-world problems. So this is our initial position, 5, 1, plus time, and it's moving at a velocity of -2, 1, where I and j are units of the vector east and north respectively. Okay, so write down the vector position that the boat has traveled for 1 hour. So using this formula here, we know that my direction, my velocity per 1 unit of time is this. Okay, because it's kilometers per hour. So a single kilometer goes this far, and we want to know after 1 hour. So I'm going to replace t with 1. Okay, and then I have 1 plus -2. It gives me 3. 1 plus 1 gives me 2. Okay. Write down the position vector after 2 hours. So instead of 1, I'm going to put in 2. So I have my initial position, which is 5, 1. My velocity, which is 2, 1. And then I add those together. 5 plus 2 times -2 is -4. 5 minus 4 gives me 1. 1 plus 2, because 2 times 1 is 2, that's going to give me 3. Okay. Now if I want to find this just in terms of t, I've got my equation here. Sometimes we're going to be writing this instead of the letter r. You might see me writing this with an x and a y. Okay, and that will, depending on how we're doing it, that could be useful for solving a problem. Okay, so new question. Okay, what can be said about the x-coordinate of the displacement vector when the boat is directly north of O? So if I'm directly north of O, that's right here, directly north, I'm going to be there. So what this means, if I'm directly north of O, then the x component is going to be equal to 0. So what does that mean? I'm going to take this top row here, right? X equals 5 plus t times negative 2. I'm going to make that top row equal to 0. So x equals 5 plus negative 2t. So now we can solve for t. I can add 2t on both sides. We made that equal 0. Divide both sides by 2, and then we get this. So 2.5. And that actually makes sense if I look at my graph, because we know at 1 second we're at 3, 2. Right? That's right there. At 2 seconds, I'm at 1, 3, which is right there. At 2.5 seconds, I'm going to be right there. So it makes sense. So like, here's 1 second, here's 2 seconds, 2.5 seconds, I'm going to be there. So I hope that makes sense. Hit replay, rewind if you need to see that one again. Okay, next page. Okay, what can be said about the x and y coordinate of the displacement vector when the boat is northwest of O at 315 degrees? So if you recall with our knowledge about bearings, straight up and down is north, right? And that's 0 degrees. So if I'm going 315 degrees from O, that means I'm going to go all the way around here. Okay, so what's so special about 315? Because I'm going north and west. Because if I go 270, if I go 270 degrees, I am all the way going just due west. Now, if I'm going 315, I'm going an additional 45 degrees. Okay, so the reason that's special is that 45 degrees. So we've got we're moving at the line y equals. Oh, I wrote the wrong thing. This is y equals negative x. Okay, I'm going to just write this bigger. Y equals negative x. You should fix your paper. Okay, so what this means for we want to find out when they intersect, y equals negative x, because we want to find the value of t when the boat is northwest, exactly. So basically what I'm looking at here is I gotta use a different color here. When this distance here is the same as this distance here. Okay, well, I've given you the answer there, but that's not the value of t, okay, because we're trying to figure out the time. But we want to know when this distance here is the same as this distance here. So in the x direction, I'm going to negative. In the y direction, I'm going up. So I'm just going to call this distance here a, because I don't have a better letter. And then here, oh, I'm going to call that negative a, right? And I'm going to call this distance a. Okay, so I've got, in the x value, I've got negative a, and in the y direction, I've got a. So we're going to solve these two equations. So we've got two variables, two unknowns. So negative a equals 5 plus negative 2t. Okay, and we've got our y equation. So we have a equals 1 plus t if I'm using these two equations. Okay, so what I'm going to do here is, if I want to solve for a, I could rearrange this and I could say t equals a minus 1 if I subtract 1 on both sides. And then I can reuse this first equation here, negative a equals 5 minus 2 t, but instead of writing t, I'm going to write a minus 1. Okay, and now I can solve for a. I've got negative a equals 5 minus 2a plus 2. I can add 2a on both sides. So then negative a plus 2a gives me a. And I've got 5 plus 2 gives me 7. So I know a is equal to 7. I mean, we already knew that from the picture because I gave it to you, but sometimes you may not know this. So if they told you it was northwest, you would need to figure out that that was 7. Okay, so now I can take my original question, this one here, the x. We're taking this, I'm going to replace the x and the y with 7 and negative 7. So x is negative 7, y is 7. Okay, so my initial position was at 5, 1. My direction vector is negative 2, 1. This is the amount, the velocity vector over 1 unit of time, and t is the time that we're trying to figure out. So now I can solve for this. Either line works fine. Let's use the bottom line. 7 equals 1 plus t times 1. So if I subtract 1 on both sides, we get t equals 6. So t equals 6 hours. I could check it with the x components too. I could have done negative 7 equals 5 minus 2t. And then I could subtract 5 on both sides. And then I would get negative 12 equals negative 2t. And then I divide both sides by negative 2, and I get t equals 6 hours. So that's an alternate check. Okay. So, all right. So, conceptually, how can the motion of a particle traveling at a constant velocity be expressed, and what do the variables and parameters stand for in this representation? So the equation that we're going to be using is r equals r subscript o plus v times t. Okay, so this is the amount of time. This is initial position. And this is the motion of the particle. Okay. And this is the velocity. Okay. And remember that velocity is a direction during 1 unit of time. This is going to come back in just a minute. Okay, so this is what we're going to be using. You might want to hit pause to copy this down. Okay, next. Example 12. Okay, so using this equation, we know this is the velocity, right? Find the velocity. The position initially is 3, 4. So I'm going to replace this here with 3, 4. We're trying to find the velocity. Uh-oh. How are we going to do that? I'll just write V. Trying to find that. And then after 2 hours, we're at this position. So remember, this represents the motion of the particle. So after 2 hours, we are at this new position, 2, 8. Okay. Okay, that's our new position. Oh, that's not the best color to use, but because I'm going to use green for something else. But okay, so we were trying to find our vector here. So if I combine our like terms here, or our rows, we've got, let's subtract 3 on both sides. So then I get 2 minus 3. And let's subtract 4 on both sides, 8 minus 4. And that's going to give me V times 2. Right? If I bring this position vector to the other side of the equal sign, I would have 2 minus 3, and I would have 8 minus 4. So then my new resulting vector is going to be negative 1, 4 times 2. And then if I divide each component by 2, then I get, my velocity vector is 1/2 times negative 1 and 4. So 1/2 times that, I'm going to get negative 0.5, and 1/2 times 4 is going to give me 2. And this is my velocity vector. So this is the velocity during 1 unit of time. This is the velocity during 1 unit of time. Okay, now we want to find the speed. So remember, the speed is the magnitude of the velocity. So speed equals the magnitude of the velocity. So that's going to be equal to negative 0.5 squared plus 2 squared. And if I put this into my calculator, my speed is 2.06 kilometers per hour. Okay. Write down an expression for the position of A after t hours. Okay, so I'm going to have r equals 3, 4. That's my initial position, plus, now I've got my velocity, negative 0.5 and 2, and then t. So I've got my velocity vector for 1 unit of time. I've got my my initial position, and this is the result vector, the resulting position. Okay. You could also write it like this: x, y equals 3, 4 plus negative 0.5, 2 times t. Okay. Sometimes you're going to want to write it either way. Okay. Find the time at which A is directly north of the harbor. So if it's north of the harbor, you got my thing going this way. If it's north of the harbor here, we have to let I can't spell. Let x equal 0 to be at that point, right? So now I'm going to take my top row here. I have x equals 3 minus 0.5 t, right? And I'm going to make x equal to 0, so I have 0 equals 3 minus 0.5 t. I can add 0.5 t on both sides. 0.5 t equals 3. And then I can divide both sides by a half, multiply both sides by 2, and we get 6 hours. So after 6 hours, we are directly above the north of the harbor. Okay. So let's just write that down. After 6 hours, we are directly north of the harbor. Okay. If you wanted to know how far north, additionally, they didn't ask this, but let's just do this. How far north? Are we? So if I wanted to know how far north are we, then I could plug in 6 into the y, because y tells us how far north, right? So then I would say y equals 4 plus 2t, and I'm going to plug in 6 in for t, and I would say y equals 4 plus 2 times 6, because y tells us how far north we go. So y equals 4 plus 12, y equals 16 kilometers. So A is 16 kilometers north of the harbor. Sometimes they may ask you how far north. Sometimes they ask you how long it takes to get there. Okay. This is super, super important. Oh my goodness. Okay, so unit vectors. So unit vector is the length of 1 unit of time. Okay. Now, and if it's in the same direction, but in order to make it 1 unit of time, we might have to use this formula here. Okay. And the most important thing is, let's write it up here. The unit vector is the velocity with its magnitude equal to 1. Okay, it's very important. Okay, the unit vector is the velocity with its magnitude equal to 1. So I can't just use some vector that's parallel to this. I has to have a magnitude of 1. So far, all of our magnitudes have been equal to 1. And speed can be calculated with this direction. But if I want it to have a magnitude equal of 1, I'm going to have to divide it by the absolute value of b. And that's going to make sure that I've got a magnitude or a length of 1. Okay. All right. So changing the magnitude of a vector while keeping this direction is called rescaling the vector. So what we're doing here by dividing by the magnitude of b is rescaling the vector, and it's going to give us a magnitude of 1, which is called normalizing the vector. Okay, maybe rewind and listen to that part just one more time. Okay. Okay, example 13. Okay. It's a long video. Okay. So, example 13. A boat is traveling with this speed. Okay. And in the direction of this. Okay, write down the velocity vector of the boat in component form. Okay, so remember, velocity has magnitude and direction. Okay, and we're using so we know the speed already. We know the speed. We're told it here, and we've got a vector that's parallel, which is this right here. So the direction is equal to 3, 4. But this does not have a magnitude or a length of 1. And how do I know that? Because I could figure out the magnitude. The magnitude of 3, 4 is equal to the square root of 3 squared plus 4 squared. My magnitude is going to give me a length of 5. This has a magnitude of 5, and we want it to have a magnitude of 1. So to make it a unit vector. So the unit vector, to make it a magnitude of 1, remember it's equal to b divided by magnitude of b. So we're going to convert 3, 4. We're going to convert that into a unit vector. So we're going to divide it by our magnitude of 3. So we're going to have 1/5 times my direction vector, which is going to give me 0.5 times 3 gives me 0.6. 0.5, or sorry, 0.5. What the heck am I talking about? Okay, 1/5 times 3 gives me 0.6, and 1/5 times 4 gives me 0.8. Okay, so this has a magnitude of 1. Okay, so so now I'm trying to find the velocity vector. So so I've got my boat speed, which is 7.5, right? And my unit vector, we just figured out, was 0.6 in the x direction, 0.8 into the y direction. And if I multiply the speed times my unit vector, that is going to give me my velocity vector. Okay. And I think I'll do the next part in another video, in part 2. I guess it's going to be 3 parts.